Life at its simplest doesn't have eyes or ears, it can't dodge or think or even watch videos about life at its simplest. It can only do one thing: replicate itself. Yep, life at its simplest is just a series of self-replicating chemical reactions. So really, in order to understand what life is, you need to understand some chemistry. Chemistry is a property of atoms, which make up pretty much everything that you see from day to day. Every person and parasite, every waterfall and wall, every tree, toad, carp, canyon, rose and rodent, every mountain and every mouse. Now, atoms are small, really, really small. I mean, just to put it into perspective, you would need to magnify this glass by a factor of about 1 billion before you'd be able to see the atoms. Oh, so there you go. That's what a really small drop of water would look like. Well, not entirely. You see, your eyes can only see in wavelengths that are about 100 times bigger than this drop, which means the wavelength of light that your eyes are capable of seeing is incapable of resolving objects that are this small, which means that it's physically impossible for you to actually see something this small. This is just a molecular dynamics simulation built on a lot of scientific research to help the visualization of the very small. So let's go back to the invisible with this atom. Say, for instance, like an oxygen atom in water. Now, within this atom you have a nucleus, a very small nucleus, give or take 10,000 times smaller than the actual atom itself, which contains all of the positive charge and essentially all of the mass. Now, electrons are negatively charged, almost massless and very wavy particles, so when they electrostatically stick to the nucleus, they mostly do it in these stable wavy forms that we call orbitals. Now, sometimes it actually turns out that it's more favourable for two nuclei to share some electrons. That is, there is more favourable interactions between the two nuclei and their combined electrons than there is repulsion between the electrons of the two atoms and the repulsion of both of the nuclei. And when this happens, the configuration of two or more atoms stuck together in a stable form we call a molecule. Now, these configurations, for simplicity, are typically represented as a line of some sort, or another way in which we have a rough representation of the envelope of the electron density. Now, all chemistry is basically the nature of which atoms stick together, and given the different amount of positive charge the nuclei can have and the different number of electrons that they can hold, this leads to an absolutely bewildering array of molecules. Now, the universe is absolutely replete with chemistry of all sorts. However, life is a rather interesting subsection of it, in that the molecules can create replicas of themselves. And that's it. That's life at its simplest. Unless it would turn out, after 4.5 billion years of hard competition, we have no simple life left on Earth. It's just a property of self-replicating systems in an environment with limited resources, both in terms of material and energy flux. That in such circumstances, systems that replicate themselves more efficiently become more preponderous. And also, after a few billion years of this chemical turmoil, of bonds breaking and reforming, of phase separation and dissolution, that one of the structures that has emerged is your brain. The very brain that's actually currently thinking about its very chaotic chemical heritage. Now, all the life that we've yet come across is intimately tied up with water and its rather unique properties. Now, water is an exceptionally common molecule as a consequence of it being made up of the first and third most common elements in the universe. It's a very small molecule, one of the smallest, and it's very polar, which means that the electrons are rather unevenly distributed, leading to relatively positive and relatively negative portions of the molecule, and this leads to one of the most important properties of water with respect to life. I mean, let me just highlight this with an example. You see, liquids typically boil according to their molecular weight. So, butane, for instance, is a fairly reasonable gas, while octane, ironically in America called gas, has about twice the molecular weight, and is a fairly reasonable liquid at room temperature. So, as expected, methane, which is about 1/4 of the molecular weight of butane, is a very good gas at room temperature and boils at about 170 degrees Celsius below freezing. However, water has almost exactly the same mass as methane, yet it boils almost 300 degrees Celsius above it. Now, this is because in methane, the electrons configure themselves in a very symmetric fashion, leading to very little potential for charge-charge interactions, all that sort of like charges repel and opposite charges attract type stuff. However, with water, the electrons are really quite asymmetrically distributed, meaning that water has these really quite strong charge-charge type interactions between the molecules, and this leads to a great ability for the water molecules to stick to themselves and to other polar species, and this is critical in its role in life. So a reasonable metaphor here is that water is like a load of magnetic balls with a load of thermal motions, which I really can't represent here. But anyway, these magnetic balls stick together very well, whereas methane would be like a load of non-magnetic balls which tend to fly apart very easily. So when I get something else that's really quite polar, say for instance like alcohol, and inject it into water, it's like throwing a different sized magnetic ball into the mix, and as you would expect, it mixes up wonderfully and they all stick together very well. However, if I add something that isn't polar, like for instance oil, the water wants to keep interacting with itself rather than with the non-polar substance, and this excludes the water and you get these two phases. And this is the really important bit. Water wants to stick to itself and expels things that it doesn't stick very well to. And yeah, this is what's going on at a molecular level when you get something like alcohol and water mixing very well, and yet you get things like oil and water not mixing at all. So life is cellular, and one of the features of cellular life is the cell membrane. Now this is made up of something that's really not that far from detergent, in that there's this polar group on one end that really likes to interact with water, and a long non-polar chain which the water molecules want to exclude. Fairly common terms for this. Hydrophilic means that it's water-loving, and hydrophobic means that it hates water. So these detergent molecules, commonly called lipids, spontaneously arrange themselves into these bilayers, make up the cell membranes of every cell in your body. But that only gets you an inside and an outside to the cell. The business end of things is the interplay between mostly two types of molecule, essentially DNA and proteins. Now, DNA basically holds the sequence to make the proteins, including the proteins that actually facilitate the replication and repair of DNA. And it's the proteins that do most of the stuff that regulate what happens in life. And like with the cell wall, both of these systems are mediated by their interaction with water. That is, there are hydrophilic bits that it's more energetically favourable for the molecule to keep in contact with the water, and hydrophobic bits, which is more favourable for the molecules to keep out of contact with water. And then finally, of course, the system is energetically kept ticking over by a horde of smaller molecules and ions. Now that's a real simple breakdown of life. However, the details are a little bit more complicated, and this is mostly what my research entails. So I'm mostly focused on the proteins, and particularly how they fold. And that's where I'm going to pick up the story in part 2.